So there's some more detail in that than you need to know for this class. It's not a chemistry class. But I think that's helpful to at least expose you to some of this information at least once. But I'm going to give you some alternative ways of thinking about these processes. Starting with
a resting neuron.
Nope, that flow of ions. So let me introduce you to another analogy. Welcome to Club Axon. This is the hottest club for ions. But unfortunately, it's pretty hard to get into. Only the potassium ions, these K+ ions, are allowed inside. Think of these K+ ions, these potassiums, as like the Kardashians, K for Kardashian, who get to enjoy inside the club. And you have all these sodium ions, these Na pluses on the outside, and whenever they try to enter, the Kardashians are like, nah, like Na, nah, like can't enter. So this is like the resting state. This is how the club axon typically occurs. Kardashians on the inside, and then the sodium peasants on the outside. But then one night, a giant flash of lightning, aka electricity, causes the front door to suddenly be stuck open. And the sodium ions are just thrilled. They're like, yes, we can go inside the club. They rush in and they want to enjoy Club Neuron 2. Except now the Kardashians feel hella cramped and they're super annoyed. So they exit and they're like, fine, we'll just like find our new club. And so they go next door to Club Axon 2.0. But now Club Axon becomes way less cool because the Kardashians aren't there anymore. So now the sodium ions leave and the process continues. So imagine this occurring down the line of Axon Street, where you start at the cell membrane, so this little store that sells cell phones. It occurs down the line. Just picture that there's like 4 clubs in a row on this street. And it ends on this bus terminal, the Axon terminal. And it basically just occurs one at a time down this street. So you have initially Kardashians inside and the peasants, the NAs on the outside. Or I'll use real terms here. So you have potassium on the inside, sodium on the outside. Then when this action potential occurs, your potassium exits, your sodium goes in, and this kind of creates down this line. Now potassium is going to go into the next part of the axon, and sodium's going to follow it. So this occurs down the line until you finally get to the terminal. I was pretty proud of this analogy, as it might be kind of corny, but yeah, club axon. But let's actually go into the steps on how this actually occurs. So that was corny, but the key takeaway here are these main steps as we referenced in the video. So here's what a typical action potential curve looks like. There are kind of 4 main stages. So you have here in green, you have your resting potential. So this is basically what the charge looks like at rest. So this is Kardashians inside the club, the other sodium peasants on the outside. This is kind of just the normalcy of what it looks like. It happens to be at -70. It's negatively charged inside the cell at resting state. And then all of a sudden some event occurs. So this is represented by number 1 here, or AKA when the doors of the club get stuck open. So when that occurs, all of a sudden you have a bunch of positively charged sodium ions rushing in, which means that your overall potential of the cell becomes more and more and more positive because you have positive ions rushing in. And then we have the very top here, the peak. This is what's called the action potential when you have this change, this positive change in your resting state. When you get up here to about 40 millivolts, all of a sudden your channels start to close again. That club becomes a little less cool because the Kardashians have left, and the potential starts to go back down negative again. And in fact, as the video was alluding to, it goes farther than it should have. It goes a little bit lower below this line. This is called hyperpolarization. Hyper means like more, like extra extreme. So this is even more polarized, or more, an even higher difference in charge between the inside and the outside. And this forms what we call the refractory period, which you see here in blue. In this refractory period, because it's so hyperpolarized, the cell has to like get back to normal state again before it can do anything else. So this is a time period where nothing can occur. It's kind of just the reset phase. And once finally the cell resets back to normal, back to -70, it's back at resting state, it's ready to receive another message. So it's resting, it gets a message, it sends it down, down the axon, goes a little too far, has to chill for a second, and then gets back up to normal where it can interact again. Keep in mind, as the video was alluding to, action potentials are all or nothing. So just like how your body and brain are text messaging to each other, as soon as you send a text message, it's all or nothing. You either send the message or you don't, and once you send it, you can't take it back. So that's like an action potential. It either occurs or it doesn't, and once it starts, it's gonna go all the way until it ends. There's no going back. So that brings us back to this analogy. Remember that toilet video at the beginning? So we're gonna watch it again, just in case you forgot what a toilet is like. And let's brainstorm how this toilet relates to a neuron firing, like an action potential. So considering these key terms that we just talked about, your resting potential, your threshold, that -55 millivolts that it has to reach for the action potential to occur, depolarization, so when you get not as polarized, you get more positive inside the cell. The all or none principle, so once it occurs, it either occurs or it doesn't. Repolarization, so going back down negative again. And refractory period, meaning you can't do anything as the neuron resets. Think about how a toilet also has these properties. Think about how you can use a toilet to help you remember these different vocab words. So we're going to play it one more time, and I want you to write down your thoughts.